Yeah, like Oleksandr, like I would say he has been writing some really nice papers in for like on topics in NISQ and like quantum, like at the boundary of quantum machine learning and all, and very relevant to like our journal club, like the works that he has done. In particular, I have like very much liked his work on this idea of inverse power iteration. So like you can keep on doing the like H inverse, like applying and find the ground state and all. That paper I liked a lot. And yeah, like his work on recently he did something on differential equations and yeah, nonlinear differential equation. And then yeah, like this talk today he will talk about like many of his works summarizing like what he has done and all. So it's a privilege to have Oleksandr here. He works at University of Exeter, and I'm very delighted to have him here. So Oleksandr, maybe you can screen share and like please, yeah, the stage.
Yes, I need to get the permission to screen share.
You don't have the permission? Okay, let me do that. Okay, sorry. Yeah, do you have it now?
Let me try. Yes, I do. Okay, so.
Awesome. Yeah.
Thanks a lot, Kishore, for inviting me, and I would be even more delighted to come to Singapore. I would fly whenever it is possible. But it's good that we can connect online. So I really like the idea of connected, even if we are far away. So in this talk, I will be presenting a couple of results, but the overall subject is designing quantum software for near-term devices. And we'll see how far away can we get, because there is a lot of information to cover, but I will concentrate on inverse iteration and Hamiltonian simulation because I feel that's more relevant to what you are doing in CQT. But of course, I hope everyone is familiar with quantum machine learning subjects, so I will try to introduce differentiable quantum circuits as well if there is time. And the starting slide usually is looking like this. We have devices that are growing in size, and quantum computing today is very different from the times when I did PhD, even though I'm not very old, because we were playing with 5-qubit devices, and now this slide should be updated pretty much every time you give talk, because 65 qubits from IBM, Google Sycamore chip, IonQ, so all systems are growing in size. But even though they appear like they improve year by year, we know that operation is noisy, and unless we can implement really deep circuits, we are staying in the near-term regime. So this noisy intermediate scale quantum computing will be very different from FTQC, and it requires some special solutions. The motivation slide, of course, and for everyone, is ability to achieve quantum supremacy. And here I will put a disclaimer, that's my own opinion, does not represent any funding bodies or companies. But in my opinion, this slide is both motivating and demotivating. Why? Because in one way we can achieve quantum supremacy for specific tasks. If you compare to classical supercomputers, you know that recently the GPUs has challenged this simulation. But let's say if we add 10 more qubits, we will be outside of the reach. And at the same time, the question arises, can we solve something useful and reach quantum advantage, so solve outstanding problem? And the difference is, for sampling, you could live with fidelities that are pretty low. So if you look for 53 qubits, the fidelities were in 0.001 overall, which is low. But if you want to do chemistry, if you want to do material science, finances, that will be that should be higher. So in some sense, we know that hardware improves, but the limits we can push in NISQ are limited. And our goal will be to develop protocols that can live with these noisy devices. The applications motivation here, I have chosen CO2 capture, so nitrogen, as you know, many examples, but the general idea will be to come up with some industrially relevant problem. For instance, for CO2 capture, you can use metal organic frameworks, but they have very complicated Hamiltonian, strong correlations. So how do you deal with that Hamiltonian? You would use a combination of quantum and classical computer to find the ground state, excited state energies, transition rates, and basically help improving CO2 capture by providing some chemistry calculations. And that will be one of the goals. So my simple introduction will be, we need a new quantum software for NISQ, and everyone knows that. I will say a couple of words about variational protocols and analog simulators, and then I will start introducing time grid methods. So that specifically will be inverse Hamiltonian iteration and also direct Hamiltonian iteration, what I call Hamiltonian's operator simulator. If there is time, I will say a couple of words about genetic ansatz construction, because this block will be related to dynamical and Hamiltonian simulation, but this will be related to parameterized quantum circuits. And I will try to introduce differentiation of quantum circuits for nonlinear differential equations. So let's start with the first part. And as I explained before, our goal will be to search for the ground state of some molecule. Since I'm a physicist, I don't care that much about how the initial Hamiltonian in terms of fermions was obtained. Let's say it's an outstanding challenging problem. We have the coefficients and these are coupled fermions. That's good enough for me. When we map it to qubit Hamiltonians, my task will be to find the way how we can prepare the ground state of this model, ideally without overhead qubits, with low circuit depths, and for a reasonable amount of measurement. So that was the challenge put, let's say, was it 5 to 10 years ago, by Matthias Streuer, who claims that chemistry will be one of the most promising use cases of quantum computing. And we can ask, what are the options? How can we find this ground state? One option is actually quantum annealing, even though it's not considered often, but the scaling is pretty bad, so you need to wait a lot to prepare the ground state. Fault-tolerant algorithms like quantum phase estimation and different variants are usually very efficient but require large depths. And there are variational protocols, variational quantum eigensolver and QAA, different ansatz that in hybrid quantum classical fashion prepare the ground state. But I will also introduce that there are quantum time grid methods that use dynamics of the system to effectively learn the low energy states of the system. And specifically, quantum inverse iterations, that's what I was working in. Quantum filter diagonalization, that was proposed by Parrish and McMahon, but we adapted it with our direct iteration and Hamiltonian approximation. And I will just say a couple of words about variational quantum eigensolver. I'm sure everyone knows how it works, but to be on the same page, what we need to do is start with some trivial state, apply ansatz as a quantum circuit which is parameterized by some angles. So let's say theta angles here, and prepare it as an approximation of the ground state. Then you will measure expectation of the Hamiltonian, get energy, and use classical optimization loop to update these angles until you reach the ground state. And here the question is, how do you implement this operation H? How do you measure the energy? That's one of the problems we would need to consider, because H is not unitary operator, so you cannot apply it directly to the state. And the answer is you cannot apply H itself, but you can split it into Pauli strings. Each can be measured individually, and you will do so-called Hamiltonian averaging procedure. You will have coefficients in front. You know how to implement Pauli strings. You just need to measure over all strings. So that's the procedure you need generally to do for variational quantum eigensolver, and I will show how we can do it differently in the future. Here is a slide with latest examples of VQE, and basically what I just want to say is that it works. And it's not a trivial question to ask, because it's variational and in some way heuristic procedure. But we can do it for reasonably, so it's not large systems, but intermediate size systems with 11 trapped ions, and recently with 12 qubits using Sycamore chip. So the size of VQE examples is growing, but what's crucial is the scaling, because we don't know how it will scale up into larger system sizes. And even if we forget about noise, if we forget about the measurement and consider ideal state vector simulation, the big question remains: can we find optimal angles even for large system sizes? So not 12, but 50 qubits. That's an open challenge. And here is the list of problems you need to overcome.
Sorry, can I ask a question, Oleksandr?
Sure, sure.
So in the previous, this is more like, so the largest system they have simulated is 12 qubit. With VQE, is that correct? Okay.
Yes.
And here, when you are plotting energy versus reaction coordinate, so you change the reaction coordinate and then you run the VQE for that one. Is it the way they get this plot, the second plot?
So the second plot, you can understand that it's in a more conventional form. It will be like energy profile of hydrogen. So large energy before, then it goes deep and increases. And for diazine studies, you just don't have distance between bond distance between let's say 2 hydrogen atoms or some other atoms, but you change the angle. And each point you want to find the ground state energy of the system. And specifically they search for Hartree-Fock, so mean field ground state, but using the VQE procedure. So it's I would say experimentally it's already very challenging to get for 12 qubits I don't think it's a chemical precision, but it's a pretty high precision for VQE. So it's a good, nice step, but the question is, can you repeat the same but for 20 qubits? Or how would it scale even in the absence of noise? I don't feel we know this scaling, and anyone showed that you can.
I think there was a paper, I think last year around December by what's the name? Yeah, from Zapata. So they they looked at the scaling, more like for the chemical accuracy and all. And as it turns out, even to simulate methane, they take 1.7 days. And if you want to simulate, let's say, ethanol, you have to go for 71 days or something.
Yeah. But I've seen
just
scaling
to get a single energy point.
In the years. So it's because if you have vanishing gradient problem, and that's what I should be introducing here, is that the problems which you face is first that not always you have good ansatz choice. So I've seen example and tried myself. If you get a very nice ansatz that parameterizes your system well with few angles, you easily reach the ground state. But if you don't know these ansatz, if it's not chemically motivated by hardware efficient, it will be difficult because it's a non-convex optimization. So landscape will look more like here, some nearly flat region of energy and then sharp decrease to the ground state. So how do you make efficient optimization in this landscape? It's an open question, and it's related also to the fact that we try to optimize rather deep ansatz that becomes close to some random circuit. So at one point you will hit the barren plateau and it's difficult to optimize anymore. And this, depending on the problem and ansatz, that can be close to 20 qubits already. So you could see how everything slows down. And essentially, no matter how many iterations you use, you will stay in this flat plateau. So optimization and ansatz choice are two problems one needs to solve for scaling VQE. And one more problem is measurement, because if you want to distinguish like small difference in energies, you would need to sample with using more and more measurements. And even in the absence of noise, if you don't use state vector simulator but sampling, you would see that simulation will take more and more time as you increase the system size, and actually may take exponentially many samples. So how do you change this? You can change it by choosing the different way of measuring energy. And the question behind is, how does it scale? So let's look at specific examples. And I would like to introduce quantum inverse power iteration as the step to overcome optimization issues. So variational quantum eigensolver, I should say, it works. It works nicely for NISQ systems, but if you push it to a large number of qubits, that is a challenge. So I was thinking, how can you rewrite it? And that was the first, let's say, idea that came out. So to explain how it works, I will start with direct power iteration. So if you have some matrix A and you apply it to eigenstate Q, you will get an eigenvalue lambda. If you apply a power of matrix A to the power of K to the eigenstate, you will get eigenvector lambda to the power of K. But what if you start with initial state, which is not an eigenstate? Then it is superposition of different eigenstates, which with a separate eigenvalue, and we can order them. So if you act once with your matrix, you will get in front with the coefficients, you will get eigenvalues, lambda 1, lambda 2, etc. If you apply it k times, you will get lambda 1 to the power of k, lambda 2 to the power of k, etc. And it means by pulling out the dominant part, the largest eigenvalue outside, you will have your eigenvector q1 for the same eigenvalue, and q2 and qn, etc., will be suppressed by the ratio of second dominant to dominant eigenvalue. And if it is a gap system, that's often in case of the chemistry, you will have these terms being small and you reach the ground state. So that's how actually in many cases, like with modifications, quantum chemistry packages work for classical software. You just do iterations, and it will be Lanczos iterations, it will be some modifications, but that's what you do. Notice that I was talking about dominant eigenvalue, but if you invert A and say to the A to the power of minus K, you will be searching for smallest eigenvalue, and that will lead you to the ground state estimation. when I was thinking about this algorithm, that was actually classically inspired. And that's usually people talk about quantum inspired algorithms for classical. But here it's, you take a classical algorithm, you ask, how would you do it classically, and then rewrite it in the quantum way. And the trick to rewrite it will be to find how the inverse of the Hamiltonian looks in terms of evolution operators, because in quantum mechanics, the only thing we can do well is apply unitary evolution. We can evolve the system and of course measure, but until you measure, it should be all unitary. So the goal is to take this unitary part as a exponent generated by h with some complex phase, but add some filter which turns it into the inverse of the Hamiltonian. So this double integration you could see as some filter filters that can convert it into the resolvent. And I can rewrite this integration as the summation with some step and some phase. There will be prefactor in front and the unitary operator itself. So that's the quantum part, and this will be some classical post-processing, some coefficients in front. But
so basically you are trying to write H inverse as linear combination of unitary.
Exactly.
Wow.
And that's what it is. So linear combination of unitaries by Childs, Kothari, and Soma was used, for instance, to solve linear systems of equation, and the same for Hamiltonian dynamic simulation. So we can say this is nothing but some phase, which I call phi KL, and some coefficients in front, which we classically just calculate. And this linear combination of unitaries, that's what we can implement if we use Ancilla-based implementation. So prepare, select the protocol you can figure out, but it's it requires deep circuits. So immediately, is it applicable directly to NISQ? Not so much. So I was thinking about a different strategy, which is apply each unitary separately. It doesn't have the same power as full LCU approach, but that's what you can use in the NISQ era. And the details are in the paper published last year.
So you should require like ability to prepare each of the individual exponential of minus phi KL h cap.
Yeah, exactly. So what you require is not just state preparation in this case. I go one step beyond and say the eigenvalue lambda. I know if I apply many times inverse operator to psi, I will prepare some approximate eigenstate. And then what I want to estimate is the energy of this eigenstate. So I will plug in my psi KL, which is the action of LCU on initial state, and measure the energy. And I will see that because LCU is linear combination of unitaries, is not unitary operator itself, I get some denominator which accounts for the change of the norm. But in the numerator, I will get this similar overlap with the Hamiltonian itself. And so far, I don't specify how I implement it. I'll just say, okay, let's imagine we do Hamiltonian averaging. So that's the full story. I see that to find the low energy properties, I just need to evolve the state psi naught, measure the overlap with psi naught, and with different phases and different coefficients. And so far, apart from just this decomposition and coefficients, which you will multiply, I could see that the only required resource is apply Hamiltonian evolution. So dynamics here represents as a resource for ground state estimation. And you may ask, how would you implement these dynamics? There are different ways, but what I want to highlight is that in analog quantum simulation, we have large system sizes, let's say hundreds of atoms that are coherently and they interact with each other and they are manipulated by light in coherent fashion. And already in 2012, Immanuel Bloch was talking about quantum supremacy because they managed to find properties, dynamics of BoseHubbard model for longer times than it's possible with matrix product states. But you could also imagine Rydberg atom chains from Lukin lab and Chris Monroe's lab, where they study dynamics in the system for rather long times, difficult to do classically. And even more exciting result is for Fermi-Hubbard model, because the lab of Marcus Greiner in Harvard does the following. They can prepare the lattice of fermions that are interacting. They can measure dynamics in the system, but what they cannot do immediately is to lower the temperature. So the major question is, can you actually go down to the wave superconductant phase? Can you test it, or Fermi liquid phase? This all requires low temperature. And the question to me, can we lower this temperature if we don't have variational procedure, if we don't have gate-based computer, but just analog quantum simulation? And my answer will be yes, if you know how to do the dynamics and measure overlaps. So let's recap the quantum inverse iteration. We start with some initial state and we decompose the inverse Hamiltonian to some power as a linear combination of unitaries. We will apply this operator to initial state and get some approximate eigenstate and measure the, by some composition of wave function overlaps, we will measure the energy. So the good part is that it's not variational and it can work with analog type simulators. That would be the main pros. If you do analog type, you don't have gate decomposition, and in principle, the converges in the same as for phase estimation, because you essentially use Hamiltonian dynamics to get there. So these are all good points. If we do not have analog simulator, the problem is you require tertorization, and tertorization, of course, will lead to longer depths. To measure overlaps, you will require something like a swap test, so it increases at least twice your system or the depths. And also the problem, it assumes Hamiltonian averaging, but I will show how this can be changed in the future. How do we measure overlap? One quick slide. In general, it's not easy. And if you ever looked, how would you measure the overlap between initial state and the time propagated state? There are few options, but it's more challenging than just Hamiltonian averaging. One option I presented is repeat the same calculation for different initial states, use one state as a reference, and if you have this reference state, you can recover it without overhead in terms of qubits. But more conventional way will be to use the swap test from Horodetsky and Eckert, where you have ancilla qubit, you have two registers with different systems you want to overlap, and doing controlled swap, you can measure this overlap. Second way is destructive swap test. You have state psi and phi, you do the controlled knot operation on these states, measure the outcome, and combine it into the overlap. But what's more exciting, that you can actually do it without gate decomposition if you use so-called many-body interferometry. So this Fermi-Hubbard and BoseHubbard models, where the researchers studied entanglement entropy in the system. And entanglement entropy can be related to the possibility of measuring overlaps. So what they did is some kind of beam splitter-like interaction that takes two copies of the systems, makes them interact, and essentially you will find the overlap between these two states from the interaction. So that's my vision. How would you proceed with wave function overlap for analog simulators? Now let me give you some examples of how does it work. So first example will be chemistry and molecular hydrogen and beryllium hydrate, but then I will also show results for BoseHubbard chain. So we start always by postulating what is the Hamiltonian of the system, and here I immediately do the mapping from the fermionic basis using the Jordan-Wigner, so we have this 4-qubit Hamiltonian. Then we assume first that we know how to simulate the dynamics, and later I show how it's done in practice. We study the dependence of convergence, so how with each new power of your inverse Hamiltonian, how you come closer to the ground state. And I also introduce what's called a maximal propagation phase, because you remember I said that this operator that I want to apply is a combination of some coefficients, but also some phases phi, k, l, h. So the larger the phase, the longer time you need to simulate, the more costly is the procedure. So I want to find how small can be the total phase until which you propagate. And that will be my effective gate count. So here is the result for 4 qubits. Ideally, if you have full inverse Hamiltonian, so you can just calculate it classically and apply to the state, you will see exponential convergence. So you will, with each new iteration, which is not optimization step, but just each new power of inverse Hamiltonian, you come closer to the ground state, and you just need few to converge to some chemical precision. Then if you actually decompose it, there will be few limiting cases. One is you decompose it into some number of terms, but your maximal propagation phase is small. And you could see you do not reach the chemical accuracy because you don't learn anything about the structure of your Hamiltonian. But if you improve it, at a certain point, it comes closer and closer to the ideal operation. We can also look not in terms of the energy precision, but in terms of what's the trace distance between my ideal inverse Hamiltonian and approximated one. And you could see with each iteration, it's more difficult to approximate the inverse Hamiltonian. That's very much expected because it also comes from the scaling of LCU approaches.
So how do we approximate the Hamiltonian? Like, sorry, maybe I missed something.
Let's return back to this slide. So in inverse Hamiltonian, you would approximate as some sum of coefficients times the unitary operator so you can generated by this Hamiltonian.
You take coefficients into account, and maybe the largest one, maybe you can.
Yeah. And this is exactly the largest one. So you say, I have my and mz steps in the grid. I have the size of each step. So the product of maximal number of steps and each step will give me a phase. But Kishore, you are right. I didn't say anything how would I do this Hamiltonian evolution. I just said, imagine that we have access to this Hamiltonian evolution.
Actually, maybe after talk, I will talk to you because that's something I'm working on. It's like, it's very relevant, this approximation idea. So like quite interesting, I would say.
Okay, excellent. So here I just wanted to say that if we have ideal dynamics, but we still use this decomposition, it works and it works if you evolve it for longer time. There was some specific dependence on the maximal phase, and it's related to which Hamiltonian you take. So it does not appear in the trace distance, but it appears in energy, because some phases are working better for specific molecular hydrogen Hamiltonian. It changes if you use different molecule. But next question is, how do you get this evolution? And if it's not available in analog simulator, you will need to use a Suzuki trotter decomposition. So I trotterize the dynamics by applying different parts of the Hamiltonian. In this case, there will be just few because many terms commute with each other. And what I could see as a number of trotter steps, everything converges nicely, even with few trotter steps. The main condition is that the maximal phase cannot be small. So you need to go to larger. And basically, the decomposition is giving you higher error than trotterization itself. And you could also study how everything depends on the trotter distance and maximal phase as a density plot. So that was one result showing that you can do trotterization. Of course, it will grow as system size increase. You will spend more and more gates, but that's a price to pay. If you have analog simulation, evolution kind of comes for free, because you just say, that's my Hamiltonian. I cannot modify it much, but I can just wait for a few microseconds if it's atomic system and see what happens. Second point, I do not have a slide, but what I studied is the noise properties. And using wave function Monte Carlo, I have shown that yes, you can do it with limited noise, and also can use error mitigation by choosing systems with different noise level. If we go to beryllium hydrate with 8 qubits, we could see that ideal inverse converges well. You need to increase the maximal phase of propagation if you want to study this larger system size. And the reason behind is that inverting Hamiltonian depends on the condition number of the Hamiltonian. So that's different for beryllium, and it's a more challenging case. But you would still see the convergence to chemical precision. And if I go to example of many-body Hamiltonian, let's say for material science, the first and good example is BoseHubbard model. So we have bosons hopping on the lattice and that interact with some nonlinear Kerr-type interaction. You could study the phase diagram of BoseHubbard model, and you will see what's called the Mott insulator to superfluid transition. And it's very simple. You could just see if U is very large, you are in the hardcore boson limit, because you can only have one boson at each side if you have spinless system. But if U is small and tunneling dominates, you have delocalized ground state. And the transition between the two is what you study here as a function of chemical potential mu and the ratio between tunneling and U. If you are in the Mott insulator region, you just have equal, so one atom at each side. What I do here, I simulate the dynamics of this system, use quantum inverse iteration, and prepare the approximate ground state of the model. And I always will start with a product state, which is just Mott state. And then applying a couple of iteration steps, I would see that the distance between ideal ground state and prepared drops down. And for system being close to ideal Mott insulator, the energy difference is naturally small. You don't have large difference. You have nearly the same state. But if J over U becomes 0.02, you are already past the transition. You are very close, you are already in the superfluid phase. And applying iterations, I can still prepare the state which corresponds to nearly perfect ground state. So how can we test it? First is energy difference, but that doesn't say me much. Okay, the energy drops down, very good. But correlation functions is what distinguishes Mott insulator from the superfluid phase, because in the superfluid phase, since you have larger tunneling, you make atoms talk to each other. So by preparing the initial state, so k equal 1 is like just the first iteration, you are always in the case where correlations drop quickly. But ideal operation is here. And it says that in J over U being rather large, so keep in mind that transition happens below 1, so 0.2 is already quite large ratio. These are the correlations that in a larger system size will drop polynomially, not exponentially. And by applying few more iterations, I can come closer to this case where correlations are decaying slower than it was in the multi-insulator case. Okay, so that was first part about the inverse iteration. And I just wanted to mention there are several papers appeared on the similar subjects. Some of them are published, others not. Kishore, I put a question mark because I don't really know where to put your quantum assisted eigensolver.
Yeah, I mean, it's under review at the moment. So yeah, I mean.
But it is a question mainly because here I use dynamics of the Hamiltonian, but as far as I understood, you don't use the dynamics.
So I basically was using, like this LCU idea, but, like sampling it and then like, progressively. So yeah, there are like quite like questions like which I have thought of with Toby. And this is what I was telling, like probably with you, we can discuss and see like something for future. Yeah.
Okay, excellent. So now let me continue. And I believe I don't have much time, but I can certainly describe the construction of Hamiltonian operator. So that's what we were doing with my master student. And idea was coming from the same LCU angle, but targeting the measurement problem. So we said, okay, we know how to come closer to the ground state, but we still do Hamiltonian averaging, and that doesn't scale nicely. So can we use the same approach for improving Hamiltonian averaging? And this is a slide from Bennett, Monroe, Babush, O'Brien paper that summarizes what can you do for measuring the Hamiltonian. And the simplest way will be to split your Hamiltonian for chemistry into separate Pauli strings, which is easy, but then you get n to the power of 4 terms. Each needs to be sampled separately, so that's a huge measurement overhead. But each time you sample, it's easy. You don't apply gates apart from single qubit rotations to fix the basis. So you have many terms to measure, but easy. So probably not the classical cost, but the depth is just 1. There are different methods that say we could use smaller number of partitions, but our post-processing before we do the measurement, but after the circuit, will require n squared gate count and the depth of n. So in total, you have less partitions and you have more gates to apply later. And my question is, can we actually push it to some ultimate limit where we don't have many partitions, but we sacrifice it and use a larger gate count? Where would it be possible? Again, in analog simulation, because you could apply Hamiltonian dynamics as your effective gate count, but you don't want to repeat measurements, and especially if you cannot adjust like any base you want, but only can measure certain observables. So how do we measure energy for analog simulator? And this is what we call Hamiltonian operator approximation. So we start with a propagator of the Hamiltonian and just take a time derivative. Since h is a generator, commutes with itself, you just get h in front minus ih and u. And that's what we want to use. Because if we multiply it back by the u dagger and I, we would get the Hamiltonian itself. So this is the simple differential representation of the system. And it's strangely enough, it was not considered for the specific subject. So I'm surprised that you can still kind of get this.
I didn't know about this. I mean, this is interesting. Yeah.
I feel it. Maybe it was used in a different context, but not for the simulation. And actually, the week we were like writing everything up to submit it to arXiv, another paper appeared on the same subject, very close. So we were kind of rushing to submit because, yeah, I'm surprised. But in any case, when we have this representation, the question is, of course, how do you deal with this derivative? And Hamiltonian is general. So for general Hamiltonian, you would need to do a finite differencing approach. So you take a unitary operator at some shifted time, original time, and divide by the difference. And this will scale, the error will scale as a function of delta t and what I call also the stencil order. Because if you imagine measuring the derivative, usually we just take 2 points and divide it by the distance between 2 points and the function in these 2 points. But there are more sophisticated techniques that use many points, and it helps to improve the precision. So we were introducing the stencil points, and what we say is derivative is a combination of unitary operators estimated at stencil points times some coefficients. So if I multiply everything back, I can see it's the same LCU as we had before. It's some Hamiltonian evolution, some numbers in front. And I will say it's HDiff, some differential representation of the Hamiltonian. So if I do the expectation value of this Hamiltonian, I can write it down as a sum of overlaps for different phases. And as compared to inverse iteration, I don't even need to account explicitly for normalization because that's automatically satisfied. So just measure these overlaps and different points, and you have some prediction of energy. How good is this approximation? It's a good question because it has two types of errors. First, if you cut off your series short, so of course you will be limited by the number of terms that you account. Second, by the delta t, so how small the difference will be between 2 points, because finite difference says the smaller the distance delta t, the better it is, because derivative estimation depends like you cannot take functions at 2 points that are far away, take the distance and have a derivative. You need to study it locally. But the relevant precision here will also depend on arithmetic error. Because as long as you come to 2 points that are close together and divided by this small delta t, you will amplify the numerical errors. And in classical computing, this is a known error. So they say there is an approximation error, but numerical error will be at 10 to minus 16 scale. So it's really small, but it appears and we see it in the plots. And just to test it, we will choose some spin chain with 3 to 8 qubits with Heisenberg Hamiltonian and some initial state. It's actually not that easy system to work with. We have shown that VQE will struggle for this system. Or we use the chemistry, and the standard workflow will be just take the fermionic Hamiltonian, use open fermion to write it in the qubit language, and try to find the ground state or estimate the energy of this system. And we will concentrate on H4 and H6 examples. So here are results. Energy precision at which you can estimate the energy of the Hamiltonian depends on the delta t. So the smaller the delta t, the better is the energy until you hit this level of numerical precision, which can be fixed if you, of course, like increase it to double precision. We checked it for Heisenberg chain, for hydrogen chain, and we could also see that the convergence increases with the stencil points. So the more points you take to estimate the derivative, the better it is.
So the delta t, like, for a small delta t, it's from the classical side there.
Exactly. That's from classical simulation data. And it's an interesting question. How does it manifest in the quantum case? So first, if you, in ideal world, that's what like we could simulate, but I will show in with the counting of noise, this plot will change. So similarly, you could go to like arithmetic precision, but let's see how it changes in the imperfect world. And there will be 2 points to consider. First point is the number of measurements you could do, because what we do, we measure overlaps. So for this, we have used a full swap test just for simplicity, but we could also do destructive swap test or Hadamard test. So you know that there are few options, but scaling will be the same. So we use a full swap. And we see that number of measurement that you need, of course, for higher precision, you need to increase the number of shots, and precision improves approximately like inverse of square root of number of shots. That's one consideration. But second is the influence of noise. And what we see is for delta t being large, the problem is for large delta t, you don't have a nice finite differencing because you do not see exactly the slope. So that's approximation error coming here. As you decrease delta t, your approximation error improves, but you would need to distinguish the difference between 2 points that are very close together. And then comes the influence of the sampling procedure. But also you will have a noise which is technically larger here. So it contributes for the longer you have evolution, the more noise you pick up, but it's also contributing here in the way single error at very small time will be amplified by delta t in the denominator. So if you have your spins in the Heisenberg chain flipped by some noise process, the influence of this trajectory will be amplified a lot. And that again leads to increase of the imprecision as you go to small delta t. So in the real world, we will never reach this limit of 10 to minus 16, but that's what we can, we see that it will be fine for majority of systems. Okay, so now direct iteration will use the same idea as before. I will apply powers of HK, and what I could write is differential representation of direct power iteration, and will be the same structure as before. You just need to measure the overlaps for h to the power 2k and 2k plus 1. What we find though is that approximating h to the large power of k is not stable. So it's actually quite difficult because past some large number of, like, I don't remember, probably past some 5 iterations, the errors pick up. So it was not the best for reaching the ground state. But we were looking for possible alternatives, and let me just finish by saying that quantum filter diagonalization was one of the best options. So Parrish and McMahon, they say, okay, we still can use this linear combination of unitary ansatz, but we do not fix coefficients. They are not just predefined numbers, but we use a variational procedure. It's a convex optimization problem. So you could write down the set of equations of solve it as generalized eigenvalue problem, where you have overlaps corresponding to normalization and some different types of overlaps. And they were using Hamiltonian, like Hamiltonian averaging. But what we propose to do is change this Hamiltonian averaging for another LCU, combine it all together, and you will just have much more efficient workflow of this algorithm. So that's what we did, and we see that the energy for different system sizes was 8-qubit hydrogen chain. We could reach chemical precision very quickly without with just few iterations of quantum filter diagonalization, and the energy precision which we get from approximation is not impacting it much. So we could see it's nearly the same as ideal operation. We could also improve it by adding more stencil points to the system. So Hamiltonian operation error is small, and using quantum filter diagonalization, we could study larger systems. So how far can we push it? And that's what we managed to do. We took the hydrogen chain with 12 qubits, and we prepared like 10 to minus 5 hard-to accuracy, which is much better than chemical precision within few iterations. And you don't need to have many overlaps, just 11 reference states, and overlaps between them was good enough. We also studied Fermi-Hubbard lattice, 4 sides, so 8 qubits, and we also seen nice convergence of energy. So if we took this Fermi-Hubbard lattice example, we would say that there is a setup that can give you dynamics. We know that how to measure overlaps in these systems, and the only required step is to combine propagation of the state with the overlap measurement, weight with some prefactors, and see the properties, namely the energy, but also some magnetization and correlations in the low energy case. So we will go down in temperature, but hopefully also change the doping and go into this D-wave superconductivity case. So that's the ultimate goal of this activity. And what is next? Of course, I wanted to discuss the scaling, and what we see that Hamiltonian operator approximation have small number of terms. We actually see it's constant. It doesn't need to be increased, but the gate count is actually growing because you need to simulate the dynamics. So there is a trade-off between just VQE and Hamiltonian evolution approaches. And our work is also under review. It's taken actually a long time, together with the parallel work of Seki and Yunoki, and the work is done with Tatiana Bespalova, who is my student working on the project. So conclusions will be: NISQ algorithms require new solutions for for near-term devices. We require new quantum software solutions, and variational quantum eigensolver works really well, I must say, as long as the system size is not large, but it has some issues like barren plateaus and measurement. And we were going slightly different direction by using dynamics as a resource and preparing the approximate eigenstate by inverse iteration or direct iteration. And if you use analog simulators, that can work very well. If not, if you use tertorization, that of course increases the depth and number, depth of your circuit. And the largest example we considered was 12-qubit H6 molecule, where we can prepare energy below the chemical accuracy. So that would be all from my side, and I don't have time to continue. So maybe next time we will discuss differentiable quantum circuits.
Well, I would say quite an interesting talk, Oleksandr, and like I would say very much aligned with what we have been doing here. So this 12-qubit example is simulated one or like on a quantum computer?
It's simulated one, and
so the largest one with the quantum computer at the moment is 12-qubit one, the Google group.
Yeah. And I would say that really the entry point is, can you simulate dynamics or not? Because what I discussed here has a constant overhead, which is a swap test and dynamics. But if you can do the dynamics, it becomes easier to scale to large system sizes, because like evolving 50 atoms as compared to 20 is not like much more difficult. But VQE between 20 qubits and 50 qubits will be a huge increase.
Yeah, definitely. I mean, I had some ideas, like regarding this inverse iteration, which I was trying to connect it to linear systems, but maybe like after the talk, I will talk about it like to you. So at this moment, like if you have some question, please. I think Dimitris has some question. Please unmute and ask. Yeah, somebody.
Yeah. Hi. Hi everybody. Hi Oleksandr. Good to see you again.
Yeah.
After some time. It's been almost 5 years, I guess, since back in Singapore. So just a quick question. Unfortunately, I missed quite a bits and pieces on and off. The timing is really unfortunate. It's late here, but so can you do, 1D analog stuff, using matrix product states, we can do large systems. I want to understand like the limitations and roughly how much can we push your method. What have you tried here in terms of BoseHubbard model, for example? And can you go close to the phase transition? Have you seen correlated effects and so on?
So it's difficult to go into phase transition with BoseHubbard because I would need to simulate it classically and at larger system size, which is, for my case, I used exact states simulator, so very suboptimal.
You keep everything, okay.
Yeah, but of course, you are right. You could do, if you write it as MPS and go to larger system size, you could in principle study phase transitions and like energy landscape at increasing size. So in fact, there was a study for tensor networks which uses this wave function overlaps for density of states measurement. So it's existing approach in tensor networks. In my case, it just we are not restricted to 1D in principle. So, but it's difficult to simulate classically at increasing scale. So Fermi-Hubbard.
What about long range order Hamiltonians things that have topological order or things that get more exciting? Like, did you try anything like that?
Good idea. We haven't tried, and it's. I don't see why it shouldn't work.
It should work
because we didn't see. So my worry originally was that maybe the gap will, like, if you have gapped or gapless system, that will hurt the quantum filter diagonalization. But it actually didn't. We tried both cases, so it works.
Okay.
But this is a difficulty. We don't have a hardware accessible easily, apart from IBM, yes?
Yes. And that's very noisy too. But
so we need to simulate it all classically. but going beyond 20 qubits will be always a challenge. So we kind of can predict it at small scale, but unless there is efficient classical simulator, we cannot go more, and then we need quantum hardware.
Yeah. Okay, thank you.
Good. Nice to see you, Dimitris.
Yeah.